Okay, so welcome everyone to the standard model and the beyond the standard model session. In this session, we have three speakers. They are Professor Valerie Gibson from Cavendish Laboratory, Cambridge, Professor Christophe Grojean from DAE, and Professor Greg Landsberg from Brown University. I will have brief introduction of each speaker, one by one, as their talk comes. Professor Gibson is going to talk about the status of flavor physics. Professor Gibson is a professor of high energy physics and fellow and director of the studies at Trinity College, Cambridge. She has been involved with the flavor physics for a very long time. She has been the UK spokesperson and PI of the LHCb experiment. Currently, she is the chair of the LHCb collaboration board. All of us who are from large collaboration know that it is a very, very important position. She has worked on very important experiments such as EMC effect, CP violation in the kaon system in Na31 at CERN, and she has worked on silicon microvertex detector and B physics measurement at the OPAL experiment. She is also currently the University Gender Equality Champion STEM. For last 2 hours, we have been just discussing, Professor Gibson, the STEM and the gender problem into our community in India. So that is a very, very important role that you play in your university. And perhaps sometime later, we could learn something from you there too. So Professor Gibson.
Thank you very much. Can you share my slides, please? That's excellent. Thank you. So thank you, first of all, for inviting me to give this talk. I'm going to tell you a little bit about heavy flavor physics and the experimental status of heavy flavor physics. And I'll leave Christophe to discuss any of the theoretical implications. Hello from Cambridge, England, and I hope you can see or at least hear me okay. It would have been great to be with you now in India, but unfortunately I'm stuck here as we all are stuck where we are. I'd just like to start actually with a little brief introduction to flavor physics and why study flavor at all. There's a few key questions that we would like answering. First of all, why there are 3 generations, the large hierarchy of masses. For example, there's 5 orders of magnitude between the electron and top quark mass. We also would like to know a little bit about the origin of neutrino mass and also the origin of the different mass matrices. I can see that the neutrino mass is so small that it's disappeared in translation of my slide. And there's a connection between the flavor puzzle, if you like, and the electroweak hierarchy, because we know that the top and the bottom and the tau are connected to the Higgs electroweak sector. Also, there's the key open questions. So what is dark matter? And also the baryon asymmetry in the universe. So the matter-antimatter asymmetry and the new sources of CP violation. I think you need to change my slide. Next one. There we go. So we know that new physics must exist, but the question is what is the energy scale? So next slide. You can treat the standard model, if you like, as a low energy effective theory. And if you do that, then in a model independent way, you can write down the amplitude for new physics as it is in the equation on the slide. And it's related to the couplings. So you've got the standard model couplings and the electroweak scale, and also the new physics couplings and the new physics scale. So new physics can have a big impact, even if the new physics scale is much bigger than the electroweak scale. And it's also more visible in flavor changing neutral currents due to extra loop factors. So the diagram there, the Feynman diagram there, is a BB bar mixing diagram. And you can do a quick calculation. If you calculate the standard model coupling there, then it's about 10 to the minus 6. So that sort of gives you some indication of the reach of flavor physics and indeed flavor changing neutral currents. if you take the equivalent lambda squared over the new physics couplings, it's about 10 to the 3 TeV all squared. So one of the main things within flavor physics is that you need precision. You need high precision measurements to see the effects of new physics within the flavor. Next slide. But flavor physics is a marathon, it's not a sprint. And you can just look at previous measurements. So if you look at years from indirect observations, if you like, to direct observations, then you can see that there's periods of time. For example, the effects of the top quark and the Higgs boson were known about 5–10 years before they were actually discovered directly. So it's a marathon and not a sprint. Next slide, please. Now, the key experiments prior to the LHC, so this is sort of early the 21st century, were the B factory experiments, the E+E- B factory experiments, which ran for about 10 years. And they sat at the ε4s. And they discovered CP violation, first of all, in the B system, which is a great discovery and should really be recognized as such, and established the CKM mechanism as well. There were other E+E- machines like Argus, LEP, Clio, and so on. And then we have the collider experiments, so the early 21st century collider experiments at the Tevatron, which was CDF and D0. And they also ran for about 10 years. And they established BS mixing, discovery of the top quark, of course, the B sub C and sine 2 beta S, which I'll come to later. But most importantly, they demonstrated the capabilities of doing flavor physics at hadron colliders. Next slide. And now, of course, we go into the new generation of experiments. So just recently, Bell 2 has started and has been taking physics data from 2019. So once again, Bell 2 is an E+E- experiment at the ε4s. And here's a picture of it. But I'll leave all the details for you to look at later. But this is a slide from Beauty 2020 from Toru Lijima. Next slide, please. And one of the main drivers to Bell 2, of course, is the fact that SuperKEK B has a nano beam scheme, and the beta star for the beam has reduced by a factor of order of about 20, which really means that the luminosity is much bigger, sort of 2.5 10 to the 34 centimeter squared per second, which means that the Bell 2 should reach about 50 inverse attobars of data, which is about 50 times the amount of Bell. And already with just the little bit of data that they have, you can see with the luminosity plot in front of you, that they have about 10% of the Bell data so far, with just a small amount of running so far. So there's great prospects for Bell 2. Next slide. And then that brings us to the key experiments at the LHC. So the main one there in flavor physics is the LHC-B experiment, which is a dedicated heavy flavor experiment. And also we have Atlas and CMS, of course, which are the high PT experiments. And here we are really making precision measurements of the CKM parameters and searching for new physics in CP violating phases and rare decays. But not only that, there is really a broad program of physics at the LHC and LHC-B as well, including electroweak physics, heavy ions, and so on, which I really don't have time to go into today. So next slide. And here is just the luminosity plots from the 3 experiments. So this is the total integrated luminosities taken so far for run 1 and run 2 at the LHC. And you can see that LHC-B there is 9 inverse femtobarns. Remember, LHC-B runs at a lower luminosity than Atlas and CMS, but it also has the luminosity leveling, which means that the luminosity is constant throughout the data taking. So that really reduces the systematic uncertainties to a level which is makes precision measurements very, very good. Next slide. And also Atlas and CMS, they have collected large data sets with dimuon triggers, which allows them to make measurements in the flavor physics arena as well. and some of the measurements we will be talking about today. So here you can see the dimuon invariant mass distributions for ATLAS and CMS. So the LHC is ideal place to do flavor physics. Next slide. It's also a B hadron factory. There's a huge number of different sorts of B hadrons, and here are just a few which have been discovered in 2020. So we've discovered lots of excited omega B states, psi B states, B sub C states, BS states, lambda B states, a huge number, and as well as all of the different B species that you already know about. So I'm not going to go into detail about those, except if you go on to the next slide, you'll see that the LHC is also an exotic hadron factory. So we've discovered a new tetraquark state recently, which is a 4-charm quark state. So that was discovered in pairs of dimuons with high PT. And then also the discovery of the pentaquark. So here is three pentaquark states were discovered, the P sub C, which is a D-UU CC bar state. And that was discovered in lambda B going to J psi proton kaon decays. And one thing to note here is the peaks in the bottom left-hand plot. You can see just sit around threshold, which sort of supports a molecular pentaquark state, sort of with a meson-baryon substructure. But what that also does is you expect the pentaquark to decay to E to C protons, and that's expected with a rate 10 times those already discovered. And so LHCb has already started searching for these types of decay. So this is one of the, on the bottom right, is one of the latest measurements from LHCb. So overall at the LHC and LHCb in particular, as far as all these new states are concerned, more than 50 new particles have been discovered in flavor physics since the start of the LHC. So it's a huge number of discoveries, not only the Higgs boson, of course, but all of these new exotic and different B species. And also in the charm sector as well, which I don't have time to talk about today. Next slide. So what I would like to focus on today will be the latest news from the quark flavor mixing and rare decays within the B system. So just a quick overview of that. In the standard model, a fundamental consequence, of course, of the Yukawa couplings and the electroweak symmetry breaking, given the 3 generations, is you get the CKM quark mixing matrix, which enters into the charge current Lagrangian. So the CKM theory of the standard model is highly predictive. There's a huge range of phenomena over a massive energy scale with only 4 parameters. It's hierarchical in the sense that the quark masses have hierarchy, and which is very distinctive to the standard model and not necessarily replicated in extended theories. And also it's the only source of matter-antimatter asymmetry, i.e. CP violation, in the standard model, given if you have the neutrino mass and the theta QCD equal to 0. And all of that can be accommodated by a single complex phase in the CKM matrix. Next slide, please. So the quark flavor mixing is sort of encapsulated in the thing called the unitarity triangle, which I have drawn here. And it's just coming from the unitarity of the matrix. So the CKM phenomenology has been extensively tested over more than 30 years, and it's very impressive achievements from all of the quark flavor experiments. So all of the ones I've mentioned at the B factories, the E+E- machines, the Tevatron, proton, antiproton, and now the LHC, as well as new developments in theory, particularly lattice QCD. And here you can see 3 pictures of the unitarity triangle over the last 17 years now. So from 2003, you can see that was just after the end of the B factories, and that's the sort of status of measurements then. 2007 was just before the start of the LHC, and you can see there in particular the angle gamma, which I'll come to in a minute, was not very well measured fact, hardly measured at all at that time. And now here we are in 2020, where you can see the effect of the LHC measurements and also the improved theory measurements. Having said that, also the B factories are still producing measurements today. Next slide, please. So the CKM matrix is complex, which means that there are phases that enter into the matrix elements. And the main one there is the angle gamma, which is the relative phase between B to C and B to U transitions in B quark decays. The other thing to note is that the neutral Bs undertake B mixing. So that means that the physical eigenstates are actually mixtures of the weak eigenstates. And the delta M there is just the difference in mass between the physical eigenstates, the heavy and light physical eigenstates. And the other two angles which I've noted in the CKM matrix there are angle beta and also angle beta S, which is the phase that appears in the decay, taking into account the mixing. So those are the three of the angles which I'd like to discuss further today. And one other thing is the CP violation, of course. So CP violation occurs if you have the rate of a B going to the final state is not equal to the rate of the B bar going to the final state. And that requires, first of all, the initial state to decay to a final state via at least two amplitudes, or decay paths, one of which is suppressed by a factor R, which you can see on the plot at the bottom of the slide. And also it requires that there's a relative strong phase, which I've labeled here delta, which has the same sign under the CP transformation. And then a relative weak phase phi, which changes sign under the CP transformation. And quite often CP violation, rather than just looking at the direct rates, is expressed in terms of asymmetry, which is the difference in the rates over the sum. And that reduces any systematic uncertainties when you're doing experimental measurements. Next slide, please. Next slide, sorry. And here is an example of CP violation. So this is interference between mixing and decay. This is in a golden decay mode, which is the B0 going to J psi Ks. And you can see at the top Feynman diagrams there, you have the decay, direct decay of the B0, and then you have the decay of the B0 having gone through B mixing. So it becomes a B bar before it decays. And then on the bottom Feynman diagrams, which is the CP operation, you have exactly the same diagrams, but between them, you have a difference of plus or minus 2 beta in the phase. And you can see the effect of that when you add up the amplitudes. The total amplitude is going to be different between the two decay routes, given by this angle 2 beta. Next slide, please. And so how you measure 2 beta, or you measure the sign of 2 beta, it's done from the time dependence of B and B bar going to J psi Ks in the simplest form. And here the formula there is the decay rate, which is written in terms of a time difference. So it's written in terms of the difference between the time difference between the B decaying to a CP eigenstate and that of the B, which you use to tag the flavour at production, at decay, sorry. So that's the formula, and this is the what you see below there. There's two parameters in there. There's SF and AF. So SF is the thing that's related to sine 2 beta, and AF is the is 0 in the standard model. So on the left-hand side, you see the most precise measurement of sine 2 beta from Bell, which has been split out into CP odd and CP even final eigenstates. And also with a B0 and B0 bar tag. And you can see on the right-hand side, the first measurement of sine 2 beta from Bell 2, with just a small amount of data, is really beginning to, well, first of all, it agrees with the previous measurements, which is a good thing, but also it's just with this very little amount of data shows that BEL2 is well en route to achieving the precision that is expected. Next slide, please. And also in the BS system, very similarly, you have the golden decay mode BS to J psi phi. And here you can look at the phi decaying to 2 pions or 2 kaons. Or indeed, you don't have to look at the phi at all. You can just look at the generic J psi pi pi, J psi kk decays. And this is what the LHC experiments have done. And this is just a summary of the phase beta S, sine 2 beta S, against the delta gamma S, which is the difference in the lifetimes between the decay rates between the heavy and light eigenstates of the BS. And you have there the standard model prediction as well, and you can see that everything is agreeing very well now. Next slide, please. That brings me on to time-dependent CP violation in BS decays. So CP violation in the BS system, rather than the B0 system, was first observed in 2013 by LHCb in BS going to K pi decays. And now in 2020, we have a huge number of BS decays, either going to, or B0 decays going to be pi plus pi minus, K plus K minus, K plus pi minus, and pi plus K minus. And this really these two plots here really show you the strength of the particle ID within LHCb, where you can pick out these individual decay modes. So on the left there, you have the B0 going to pi plus pi minus, and on the right, you have the BS going to K plus K minus. Next slide, please. And so you can take those events and you can form the asymmetry, and the formula for the asymmetry is at the top of the slide. And so the coefficients there, the CF and the SF, describe the magnitude and phase of the oscillation of the B0 and B0S. And the asymmetry A delta gamma describes how the physical eigenstates, sort of the composition of those changes with time. And there you can see the asymmetries in B0 to pi plus pi minus, and the BS to K plus K minus. And just note actually the scale on the x-axis with the different oscillation periods for the B0 and B0S. You can see you've got a 10 picoseconds for the B0 and 0.4 picoseconds for the BS there. So the coefficients have been measured, and they're different for the BS system, different from the no CP violation by more than 6 sigma. And so this is now the first observation of time-dependent CP violation in the BS system from LHCb. Next slide, please. That also brings me to something called the K-pi puzzle. So in these B to HH decays, there's been a long-standing discrepancy between the CP asymmetries measured in B plus going to K plus pi 0 and B0 going to K plus pi minus decays. And you would expect these to be equal just from isospin arguments. But prior to the LHC, the difference in the asymmetries between those two decay modes was measured to be 6 sigma different from 5.9 sigma different from 0. So I want to tell you what the current status of that is. And if you look at the Feynman diagrams for the decay mode, so you've got the B0 going to K pi and the B plus going to K pi below, then you'd expect the interference just between the tree and the penguin diagrams. But in the B plus case, next slide please, you also get the color suppressed and electroweak penguins, which contribute to the B plus K going to K plus pi 0. Next slide. So there's been a first analysis of this at the LHC, from LHCb, which is a first analysis of one-track B decays at a hadron collider. So there's no secondary vertex here. All it's doing is using precision tracking and a dedicated trigger. And you can see the top plots here are preliminary plots from LHCb, where we've got B plus going to K plus pi 0 and the B minus going to K minus pi 0. And the CP asymmetry for B plus going to K plus pi 0 decays is 0.025, and given all those numbers as well. So you've got the statistical, systematic and external input to that measurement. And from the B0 going to K plus pi minus observation, you can also see a huge asymmetry there between the two plots on the bottom of the slide, which gives you an 8% overall CP asymmetry for those types of decay. So you can put those two measurements together. Next slide, please. And you can update the world average of the difference between the CP asymmetry of B plus going to K plus pi 0 and B0 going to K plus pi minus. And now it's increased. It's now 8.2 sigma observation of the difference between those CP asymmetries. So the K-pi puzzle still exists. There's one thing that you can also do is you can relate all of the asymmetries and lifetimes and branching fractions by this sort of sum rule, which is given there on the slide. And you can turn that around and predict what you'd expect the CP asymmetry to be in B0 to K0 pi 0 decays, which is a very difficult thing to measure. And you can see that's 5.5 sigma away from what you'd expect. So that tension can be resolved with sort of enhancing the color suppressed trees or new physics in the lecture week penguins. And this is why this is so interesting, that we're wondering whether where this K-pi puzzle is coming from. And one thing that's nice, what the direct measurement of the B0 to K0 pi 0 is a key component of the Bell 2 physics program. So the little plot here sort of shows you the impact of Bell 2 on this measurement, where you've got the CP asymmetry on the x-axis of B0 going to K0 pi 0 against sine 2 beta from K0 pi 0. And the data point there is the direct measurement of those two. And you can see the effect of Bell 2, which is given by the red cross there. That's with 50 inverse attobons of data. And then you've got the constraints coming from the indirect measurements, which is the orange band, and then what you'd project from 50 inverse attobons of data as well. So this is one to keep an eye on for the future, just to see how this develops, and also the theoretical implications of the K-pi puzzle. Next slide, please. So that brings me on to the angle gamma, which is measured from the interference of B to C and B to U tree level B to DK decays, and the two Feynman diagrams are given there. And there's a small theoretical uncertainty here, which is negligible. It's the order of 10 to the minus 7. And the way that the angle gamma is measured, it's measured from a combination of many different decay modes, which sort of sit in three categories. The first being time integrated asymmetries in B to DK decays, for example, with the D going to either CP even eigenstates, which is called the GLW measurement, or non-CP eigenstates, which is the ADS measurement. Or it can be measured from a Dallas plot analysis of the D decay itself into KSHH, which is called the Dalits or BPGGSZ method. Or it can be measured in time-dependent analysis, such as BS to DSK, or BS to DSK pi pi, B0 to D pi, and so on. So I want to give you one example of each of these different methods, and these are the latest measurements that are coming out of the LHC or LHCb today. So next slide, please. So this is the gamma from time-integrated asymmetries using the full LHCb data set. And you can see in the top two plots, you have the CP even final states of the D going to K plus K minus. And there you get the interference through the different B decays. And on the bottom, you have the non-CP eigenstate final states, where you get the interference through the different D decays. And this analysis is the first time that the partially reconstructed D star going to either D pi 0 or gamma modes are included as well. And it's a data-driven measurement in the sense that the shapes of these distributions, mass distributions and efficiencies are coming from control channels. Next slide. This is an example of the latest measurement of gamma from the Odisha plot analysis. So once again, this is using the full LHCb data set. On the left-hand side, you can see the B to DK signal events. So there's about 15,000 events in there. And on the right, you can see the B to D pi control channel events with about 210K events and how clean those distributions are. So the B to DK is where you have significant CP violation, and the B to D pi is where you've got this high statistics sample, very low CP violation, and you can use that for a data-driven acceptance. Next slide. And this is the Dalitz distribution I took from Beauty 2020, where you can now see that the CP asymmetry is visible by eye, and those red and blue rectangles sort of focus your eye on the areas that you should be looking at to see a difference between the B minus and the B plus going to DK, where the D is going to KS pi plus pi minus. So this is the Dalitz plot of the D going to KS pi plus pi minus. And in the B to DK, of course, you've got the large contribution from B to U decays, and RB, which is the ratio of the B to U to B to C amplitudes, is about 10%. Next slide. And the way that you do, one way of extracting gamma from this is using a binned model independent fit. And these sort of camouflaged butterfly Dalitz plot here shows you where the bins are, optimized bins for this analysis. And the physics parameters here, so the formula and the number of events in each of those bins is given by the physics parameters, which are X and Y, which are related to RB, the strong phase delta B and gamma. And you need to input the strong phase parameters, which are the coefficients CI and SI here. And here you take the measurements from the new measurements from BESS3, also Clio C in the past. And you have the world leading expert in BESS3 who's listening today, which is Jim Libby. So he's with you. And you take them, they're coming from experimental measurements. You input those into this binned model independent fit. And you also have the flavor specific bin yield in fractions as well, which are these Fi in the equation. So there's shared between the B to DK and B to D pi analysis. Next slide. And here you can see on the right hand side, actually, you see large CP asymmetries in certain regions of the phase space. So there's 20 bins across this Dalitz plane. And you can see in some of the bins, then you're getting quite large CP asymmetries. And then on the left-hand side, you have the X and Y, and you can see where the angle gamma comes between the X and Y in that plane there. That's how you measure them. Next slide. And then the third way of measuring gamma is from a time-dependent analysis. And here you measure, in this case, it's going BS going to DSK pi pi, where you measure gamma minus 2 beta S, but beta S you know very well from other measurements, so you can input that into this analysis. And in this decay mode, you have a high branching fraction, although you need to take into account the resonance structure in the four-body phase space of the BS. You can see a nice, on the left-hand side, the peak of the BS going to DSK pi pi. And then on the right-hand side, you can see the asymmetry as a function of the time. And so you can take that. Next slide, please. And also, sort of the side measurement of this is delta MS from this time-dependent analysis, because the control channel, the BS to DS3 pi, also provides this measurement of delta MS. And you can see on the left-hand side there, the yield of B0S and B0S bar as a function of time, and you can see beautiful BS oscillations there, and pure quantum mechanics. I just love that plot. And then on the right hand side, you've got the asymmetry as well. And so you can extract delta MS from this decay mode, because you don't have any CP violation here, or very little CP violation. And this is the world's single best measurement of delta MS now, which is 17.7 per picosecond. Next slide. So you can put all of the measurements of gamma together, and there are many decay modes that you can combine to constrain gamma. So this is the combination from LHCb. The ADS-GLW, so the time independent rates, have strong constraints on RB, delta B, and gamma, but they do include ambiguities and non-Gaussian uncertainties. The Dalitz mode breaks those ambiguities and provides the most precise single measurement. And then you've got all the different correlations between the measurements. So the combined gamma uncertainty is lower than the plane average, excuse me. And the different approaches allow for better control of the systematics. So gamma coming from LHCb is 67 plus or minus 4 degrees now, and that can compare to the overall fit of the CKM, which I've taken from CKM fitter here, which is 65.7 plus 0.9 minus 2.7 degrees. So gamma is now very well measured at the LHC. It still is dominated by the experimental uncertainties, statistical uncertainties. So there's still a long way to go on the measurement of gamma, but it's no longer the least well-known part of the CKM matrix now. Next slide, please. That brings me to VUB over VCB. There's been a long-standing tension between inclusive and exclusive measurements of VUB, which is summarized in this plot, which I took from Beauty 2020. Next slide. I realize that the time is running on, so I'll have to go a bit quicker. Bell 2 is very well prepared to measure VUB over VCB, both from inclusive decays, where you look at the endpoint region of the lepton momentum spectrum, and from exclusive tag decays as well. So there's excellent prospects there. Next slide. And also there's a first observation of BS going to K mu new decays from LHCb, which has been measured in 2 regions of Q squared. And you can see the peaks, little peaks there on the right-hand side of those 2 distributions, and its branching fraction has been measured. So this is nice. It's semi-leptonic decays at hadron colliders, which is initially wasn't thought we would be able to do, but you can see that clearly we can do that now. Next slide. And you can put that together with the BS going to D mu nu decays to extract VUB over VCB. So you just take the ratio of the number of decays, which is related to VUB over VCB. The problem here is you have to input some information from theory, so the form factors of the K minus and DS. And there's a lot of progress in calculating these form factors. It seems that a low Q, and the reason we have the 2 Q squared bins is at low Q squared, the light cone sum rule theory calculation is more accurate. In the higher Q squared bin, the lattice QCD theory calculation is more accurate. And so you can see the situation on the right-hand side is that we have the 2 measurements of VUB from BS to K mu nu decays compared to all of the other measurements in the exclusive inclusive measurements of VUB and VCB. So there's been good progress in the calculation of the form factors, although differences still need to be understood. Next slide. That brings me on to the last topic of this talk, which is the rare B decays. And in the standard model, decays involving B to S quark transitions are only allowed in loop diagrams. And the 3 sort of categories of loop diagrams are summarized in this plot, in this slide. So there's BS to mu mu, there's the electroweak penguin decays of BS to mu mu, and then there's B to S gamma. And all of the physics is sort of encapsulated in the effective Hamiltonian, where you have the operators, all of the operators for the left-handed and the right-handed parts, as well as the Wilson coefficients as well at the bottom. Next slide. And I should say that if you look at the electroweak penguins, or you look at Be to S gamma, and you look at the Q-squared invariant mass of the dilepton system in the final state, then they're sensitive to the different Wilson coefficients. So overall, the data sort of give a consistent picture here, which I've taken from Algaro, which is the latest sort of study of this. And the best fit is inconsistent with the standard model by more than 6 sigma now. That's as an assumption in that, assuming no further uncertainties on the standard model predictions. So the plot there on the right-hand side is sort of an example of a good fit, which allows for new physics in C9 with some lepton flavor universality violation for the muons as well. Next slide. So this is the status of beta mu mu. Beta mu mu is the golden decay, rare decay channel now. I wouldn't say it's very rare anymore because we've observed it, but it's been observed by all 3 of the experiments, which you can see the plots there. And the important thing about this is that new models, new physics models, can really modify the rate substantially. Next slide. And the combination has now been done of the 3 experiments. So with the run 1, run 2, and which is the 2015-2016 data. So this is a summary of that combination. In summary, the branching fraction of BS to mu mu is about 2.1 sigma below the standard model predictions. So it's still far from the theory uncertainty. So it still needs to be measured more precisely. The next step will be to measure the B0, or observe the B0 going to mu plus mu minus, which has not been done yet. And also the experiments are now measuring the effective lifetime as well, which is also sensitive to new physics. So we are eagerly waiting the full run 2 analysis for this, this decay mode. Next slide. Then we have the B to S L plus L minus. So this is the test of lepton flavor universality, which has a negligible theory uncertainty because you're taking a ratio. In fact, you take a double ratio so you can remove all the efficiencies of the electrons and muons. So you also use this J psi in the final state here as well. So this is a summary of the LHCb measurements at the top here, where you have this ratio RK, RK star, and also RPK in the B baryon system as well. So all of those seem to be lower than this standard model expectation by up to about 2.5 sigma. Bell has also produced their full analysis or full data set analysis of RK using K plus and K0S in the final state. And that's sort of consistent with the standard model and LHCb. So the precision is still limited here by statistics in all cases from the electron samples. Next slide. Then we have the angular analyses of these types of decay modes. So here we have the electroweak penguins. There's many observables in these angular analyses. And you can see some CMS results at the top, where they've extracted the forward-backward asymmetry in B to K star mu mu decays, and also the polarization of the K star in the B to K star mu mu decays as well. And then on the bottom, you have this famous observable called P5 prime, where LHCb observes a tension with the standard model in the sort of mostly in the Q-squared bins around 5 to 6, 3 to 6. And there's a preliminary result from LHCb now from the B plus going to K star plus mu minus decays as well, which is consistent with the B0 going to K star mu plus mu minus. Next slide. And then finally, there's the B to S gamma angular analysis, which provides a constraint on the photon polarization Wilson coefficient C7 or C7 prime as well. And this is the latest from LHCb here, where on the left-hand side, you can see the reconstructed decays in K star E plus E minus. And these exclusive measurements provide these strong constraints. And on the top right there, you can see that everything's consistent with the standard model predictions. And what's really nice is that BEL2 is capable of performing the inclusive measurement. And there's a plot there from Beauty 2020 from BEL2. Next slide. So just a quick comment on the outlook. Heavy flavor physics is moving rapidly to the next era with the advent of BEL2 and the LHCb upgrades and the Atlas and CMS upgrades and the high luminosity LHC. We have a full program of work which starts from working very hard to upgrade right now, but the physics data taking starts in February 2022. And then we have further upgrades as well, going on to about 2035. BEL2 will be taking data for the next 5 years at least. And so there's lots to look forward to. So just in summary, there's a large number of observables which are theoretically clean and are still statistics limited. So higher precision is really strongly motivated. For example, in sine 2 beta S, gamma, RK star. You can see there where you would expect the unitarity triangle to be in some years' time when LHCb has done their upgrade too and have collected 300 inverse femtobarns of data. There's many important phenomena which are still to be observed. For example, B0 to mu plus, mu minus. Many important new measurements will be made in the electroweak penguins and the study of P5 prime. A rich field where surprises are guaranteed. We didn't expect to discover direct charm CP violation, which I haven't mentioned today, pentaquarks, and so on. BEL2 will be able to do the inclusive B2S gamma and so on. So flavor physics probes higher mass scales than direct searches and hopefully may reveal the new physics needed to explain the mysteries of the standard model, cosmos, and everything. Right. So thank you for listening. I'm sorry I went over time.
Thank you, Professor Gibson. Questions? Okay. Sanjay, please go ahead.
Yeah, I have just general question. Well, is if you wait for 5 years, which areas or which channels LHCb will better compared to BEL2 and the other way around? Which areas BEL2 will be better than LHCb in 5 years' time?
That's a very good question. Of course, the studies have been done, but studies can be done without a knowledge of what's going to happen to the experiments and how they will perform. In principle, BEL2 should do very well in sort of the semi-leptonics and anything with neutral decay modes, pi zeros and so on. But we are seeing that LHCb can perform very well in those types of decay modes as well. So I think there's really complementary and competitive physics to be done here. I'm very excited to see both experiments perform to their best and improve all of the measurements.
Thank you. Last question.
So I know that was not an answer that you wanted to hear, but there is a summary slide actually of the comparison between BEL2 and LHCb, given all of the expected data that we take. But I don't have time to show that. But in the slides, there is a comparison there that you can have a look at.
Sure.
Dr. Datar, last question.
Yeah. Okay. What would you say is the most important signal which goes beyond the standard model from the data that has been analyzed by both LHCb and BEL? And what would that point to? In terms of,
So I'm very excited to see the updates on the lepton flavor universality tests, especially RK, which should come very soon. I think I have to leave the theorists to Christophe to comment, but the sort of two front runners for what the new physics might be are potentially leptoquarks or mu Z prime, something like that. There is also a slide in the backup which sort of summarise the current thinking on that. So those are the measurements I'd like to see, but I think there's lots of them which contribute to this indication of physics beyond the standard model. Now, if it is physics beyond the standard model, or whether it's improved theoretical calculations that we need of the standard model, that's another question.
Oh, thank you.
Thank you, Professor Gibson. Thank you for a very good talk. So now,
thank you very much. My pleasure.
Thank you, Professor Gibson. Now we move to the next speaker. The next speaker is Professor Christophe Grojean. He will talk about beyond the standard model theory. He is a member of the DAISY theory group, and he specializes in Higgs physics. And obviously we know that Higgs physics detailed study leads to beyond the standard model physics. So beyond the standard model theory, he is going to discuss. Professor Christophe Grojean, welcome. So 35 minutes for the talk, 5 minutes for the Q&A.
Okay, we'll try. Okay.
I would like you to monitor your time. Okay.
Sure. Okay, I'll do my best. So good afternoon, good evening, everybody. It's my pleasure to be with you, even though I will prefer much more to be in person with you. I mean, this very nice landscape that were in your poster, clearly. So today I would like to talk indeed about physics beyond the standard model, and maybe trying to give you a theoretical perspective on what we expect, right? Okay. So of course, physics beyond the standard model is rather elusive, and it's also a concept which is evolving with time. I mean, BSM approaches have been changed over the years of a result of experimental progress, right? So what I will focus on is discuss the connection between Higgs and physics beyond the standard model, because this is really a good motivation, you know, of why we should actually build a Higgs factory in the future after the LHC. And then I will focus about possible scenarios of physics beyond the standard model around the TV scale, because this is a very well-motivated scenario from the theoretical point of view, the connection with the hierarchy problem in particular. And actually that was the main part of what BSM used to be. I mean, if I were to give this talk 10 years ago, I would actually focus only on this part. But things have changed slightly, and now there is various ways to discover physics beyond the standard model. And I will discuss few interesting signatures of BSM at intensity frontiers, right? And as you know, I mean, the need of dark matter, maybe dark energy, also are maybe the most direct evidence, experimental evidence of the need for physics beyond the standard model. So we'll really discuss some possible scenarios of BSM in the dark sectors. And if time permits, I will also discuss the connection with gravitational waves, right? So probing the unknown, I mean, the standard model is certainly not enough. I mean, there are many questions about the universe, dark matter, dark energy, this asymmetry between matter and antimatter. And there are also a few anomalies. I mean, you have heard probably of the galactic center excess. I mean, this tension in the measurement of Hubble parameters, right? In addition, there are also several puzzling colliders data. I mean, the famous B anomalies that Valerie talked to you about in the previous talk. There is all this question of the flavour hierarchies, you know, why the muon actually is different than the electron. There is also the question of CP violation, maybe some measurement of anomalous magnetic moment of the muon or the electron, and all these things, right? And these don't fit very well within the standard model prediction, right? In addition, there are also many theoretical questions like the black hole information paradox, the question of unification, the issues of the mass hierarchy between the Wick scale and the Planck scale, the question of confinement that we don't really understand, you know, from first principle, right? So certainly there is no doubt that there is something else beyond the standard model. The question is, what actually are we looking for, and how do we search for it, right? And at the moment, I think it's fair to say that there is no clear path, you know, towards physics beyond the standard model. And really, we need a global approach, you know, with new tools to explore different horizons. And those new tools could be, I mean, coming from the cosmological frontier, from the astroparticle frontier, or the intensity frontier, or the energy frontier, right? But also we shouldn't forget that maybe these days, I mean, the best tool that will ensure big progress in science is actually a vaccine, right? So first point of the talk is the connection between Higgs and physics beyond the standard model. So, I mean, the standard model is certainly the triumph of the 20th century pillars of physics, right? Namely special relativity and quantum mechanics. And what have we learned from this combination? Well, we learn what a particle is. A particle is actually a representation of the Poincaré group. And according to the Coleman-Mandula theorem, those representations are characterized by a spin, by a mass, and by some internal quantum numbers that actually commute with spin and mass, right? And experiments show that these internal quantum numbers should at least be contained in SU3 cross SU2 cross U1, right? So this seems to be in pretty good agreement. You know, we have measured all this particle spectrum, you know, and we have assigned precisely all these quantum numbers, right? The problem is that actually this spectrum is actually incompatible with the chiral nature of the gauge symmetry, right? The fact that the left-handed electron has different quantum numbers than the right-handed electron, right? In principle, this forces the mass of the electron to vanish. In the same way, if you really want to maintain gauge invariance, then the masses of all the gauge boson has to vanish, right? So really the chiral nature of the gauge symmetry of the standard model, you know, is incompatible with the mass spectrum as we know it, right? And this fact, I mean, the chiral nature of the gauge symmetry might have something to do with, you know, with the chiral nature of that we know in life, in molecular biology. We also know that chirality is really a needed property for life to emerge. So maybe this chirality in biology is actually linked to chirality within the standard model. This is still an open question. So what is the answer to this chirality puzzle, right? The answer has been known since a few years now, is simply due to the fact that the short distance interaction are actually very different than the long distance interaction. And as a result, actually the mass of the particle are not, you know, UV quantity, but they are really infrared emergent quantity due to a non-trivial structure of the vacuum, right? And this is really something which is non-trivial. I mean, in quantum mechanics, you cannot have a spontaneous symmetry breaking, right? It's something that can occur only in quantum field theory, right? Where you will have more difficult transition between degenerate vacua, right? And this will basically lead to a nonlinear realization of the symmetry in the Hilbert space, right? So now, the vacuum of the standard model clearly breaks SU2 cross U1 down to U1 of electromagnetism. And there is one particular field which is responsible for this breaking. I mean, this is an elementary scalar field that has been discovered, and a clear manifestation of this scalar field is nothing else than the Higgs boson that has been discovered at the LHE in 2012, right? So this discovery certainly has been an important milestone for high energy physics, but at the same time, I mean, many of us should still be excited about it. I mean, you know, things is not down after the discovery. There is still a lot of questions that arise precisely because we know that the field exists, right? And actually, other people in other fields, you know, of science should also be excited about the Higgs boson. Why so? Well, first of all, because the Higgs really comes from new forces of totally different natures than the gauge interaction that were known so far, right? I mean, like electromagnetism or the weak interaction or the strong interaction are all described by gauge interaction, which are linked with local symmetries. This is not the case of the new force associated to the Higgs, right? There is no, as far as we know, there is no local symmetry associated to the Yukawa interaction, for instance. Also, those forces of the Higgs with matter are not quantized. You know, I mean, the Yukawa coupling can take arbitrary continuous values. They are not simple multiple of the Yukawa of the electron, for instance. And also those forces, as I say, are really deeply connected to the non-trivial space-time vacuum structure. Furthermore, the knowledge of the value of the Higgs coupling is really essential to our understanding of the deep structure of matter. So for instance, you know, take the mass of the proton and the mass of the neutron. You know that QCD is invariant under isospin. So you should really predict that the mass of the proton should be equal to the mass of the neutron. Of course, you have electromagnetism. I mean, proton is sensible to electromagnetism, and actually electromagnetism should make the proton a little bit heavier than the neutron. That will be a total disaster because all the nuclei will be unstable. And it's only due to the Higgs interaction with up and down quark, actually, those Yukawa interactions are such that actually the proton becomes lighter than the neutron, and then the nuclei can be finally stable and matter can exist as we know it. Also, the value of the Higgs interaction with the electron, at the end of the day, controls the mass of the electron, and the mass of the electron really sets the size of the atom, right? So it's essential to know, to be able to measure the value of the electron Yukawa to understand the size of the atom. Similarly, the value of the top quark Yukawa coupling, so the interaction between the Higgs and the top quark, actually decide the lifetime of the universe. You know that when you take into account quantum correction, the electric vacuum actually is only a metastable vacuum. There is another vacuum that develop at very large value of the Higgs field. And there is a non-trivial tunneling probability to tunnel from the electric vacuum into the true vacuum of the standard model. And the value of the top quark Yukawa actually decide of this lifetime of this tunneling time, right? Also, the value of the Higgs self-coupling, the Higgs is actually the only particle in the standard model that interact with itself, right? And the value of this self-coupling actually control the thermodynamics of the electric phase transition that took place something like 10 to minus 10 seconds after the Big Bang, right? So depending on the value of the self-coupling, we could have a first order phase transition or second order phase transition, right? So very violent phenomena with creation of bubbles, for instance, and when those bubbles collide, I mean, you could produce gravitational wave, for instance, right? But you could produce gravitational wave, but you could also produce an asymmetry between matter and antimatter, right? So why matter took over antimatter could be simply a result of this particular value of the Higgs self-coupling that could allow a first order phase transition. And finally, last example, I mean, the value of the coupling of the Higgs to the W and the Z at the end of the day sets the lifetime of the sun and the lifetime of all the stars. And I mean, quite remarkably also, the lifetime of this star is of the same order of the typical biological life, right? I mean, for life to emerge, you need several billion of years, and this turns out to be the same thing as the lifetime of the stars. So that's quite remarkable. Maybe that's an accident. Maybe there is something deep about that. We still don't know. So that's why we need to measure with high precision all the value of the Higgs couplings. Right? And I should say that all the interaction of, let's say, quarks and the lepton with the gauge field, I mean, are well understood. They are well under control because they are associated to gauge symmetry. So why, for instance, the electron interact with the photon exactly on the same way as on Earth or in the moon or on the other side of the universe is because there is a U1 gauge invariance. But this is not the case for the Higgs coupling. The Higgs coupling, I mean, take arbitrary value that, there is no underlying structure, there is no underlying symmetry. And actually, they are associated to some big puzzle that we certainly don't understand. And this is the case for each of the coupling of the Higgs. For instance, you have the mass term of the Higgs, or the quadratic term in the Lagrangian, and this is associated to the hierarchy problem. We still don't understand why this mass term is of order 100 of GeV and not of the Planck scale, as you would have expected under radiative correction. Right? The value of the Higgs self-coupling, I mean, this quartic interaction, as I say, dictates the stability of the electric vacuum. And this is a puzzle, again, that we don't understand. And finally, all this Yukawa coupling, that dictates the mass and the mixing of the different fermions, is a pattern that we don't understand. We measure them, but we have no understanding of why this mixing and this mass spectrum is like that. And furthermore, there is all the question of flavor and CP violation that remains totally unexplained, understood, right? So this is why we really need to make very precise measurement of the Higgs, right? And these are the prospect of what will be measured, about the Higgs in the future at high luminosity phase of the LHE. You will see that you will measure all the Higgs coupling with an accuracy slightly above 1%. And you can see also the correlation between, the measurement in the Higgs sector and the measurement in the electric sector and in the dye-boson sector. You are removing some of those correlations. And this will be the prospect really at future collider, and Higgs factories, etc. And you see really some good improvement over LHE by more than one order of magnitude, right? So this is really the goal of all these X factories, and what can we learn from the precise measurement of all this coupling? Well, I mean, you can use this measurement, to learn about physics beyond the standard model, for the simple reason that within the standard model, all the X coupling are fully determined in terms of quantities that have been already measured with high accuracy. For instance, G Fermi, the mass of the W, the mass of the Z, the mass of the quark, and the mass of the leptons, right? So if you're able, to measure with high accuracy all this X coupling and see a deviation compared to what is predicted by the standard model, then you will get a clear indication, of a new source, a deformation coming from physics beyond the standard model. So let's put some scale, right? I mean, you can really easily estimate the variation of the coupling of the X, relative to the standard model prediction, and it will scale like the ratio of the weak scale squared divided by the scale of new physics squared, right? So this means that if you're able to measure all this X coupling with an accuracy of 10 or 20%, as it is done nowadays at the LHE, means that you will be probing the scale of new physics up to 500 GeV or so, right? So you won't learn anything because you have already probed, the existence or the non-existence of physics beyond the standard model up to this scale. So if you really want to measure and probe directly physics beyond the standard model, at scale that haven't been probed directly at colliders, then you need to increase dramatically the sensitivity on the X coupling. And if you're able to measure those X coupling with an accuracy of 1% or 1 per mil, then you will be probing the scale of new physics up to several TeV, where basically you don't know exactly what to expect of physics beyond the standard model, right? So that's why you really need a very precise X program physics at future colliders. Unfortunately, there is many projects along this line, starting with a linear collider in Japan, and then there is a project of a circular collider with electron and positron in China, and then finally at CERN, there is another project with 100-kilometer tunnel, first of all to collide electron and positron, and to produce, something like a million of Higgs boson. And furthermore, I mean, afterwards, you will replace the electron and positron with proton to reach an energy scale of the order of 100 of TeV, where you will be really exploring scale, at distances, at short distances that have never been explored before, right? And you can really use all these colliders to perform very exquisite measurement of the X coupling. And from this measurement of the X coupling with high accuracy, then you can put some bound on, on a new particle physics beyond the standard model. For instance, if you assume that really the X is a composite object, you will expect to see many other resonances of the new strong interaction, and the measurement of the X coupling, will put some bounds of the order of 20 or 30 TeV or 40 TeV on the masses of all these new resonances, very similar to, to the meson or the baryon of QCD, right? So some scale that will be one order of magnitude larger than what you will be probing directly, by searching those new resonances directly at the 100 TeV colliders, right? So really, this will be providing unbeatable evidence for physics beyond the standard model by great measurement of in the X sectors. So let me come back now to the possible structure of new physics at the TeV scale, right? So the real question is actually, why the TeV scale? I mean, what is the scale of new physics that we are really expecting, right? So you can see that actually there is a little bit of tension. On one side, there are experimental data that is telling you that the scale of new physics should be very large, right? For instance, take flavor data. Flavor data basically don't really like flavor changing neutral current. So, some possible dimension 6 interaction among the quark and the lepton of the standard model using also the gauge boson of the standard model, those kind of dimension 6 interaction are basically forbidden if the scale of new physics is below 1,000 of TeV, right? On the other hand, you have also neutrino masses, right, that could be explained by this dimension 5 Weinberg operator. And if you put the mass scale of the neutrino masses of the order of one electron volt, then you will understand that the scale of new physics should be of the order of 10 to the 14 GeV. Furthermore, we have not seen the proton to decay. While it's possible, it's also possible, you know, in physics beyond the standard model. It's not possible, you know, if you restrict yourself with dimension 4 interaction, because at dimension 4 interaction, you cannot write interactions that are violating the baryon or the lepton number. But at the dimension 6 interaction level, you know, you can really write a contact interaction among 3 quarks and 1 electron, like this dimension 6, 4 Fermi interaction. And this will lead to fast proton decay, you know, a decay of the proton in a lifetime smaller than 10 to the 34 years, if the mass scale of this new dimension 6 interaction is actually smaller than 10 to the 16 GeV. Right? So clearly, all this experimental data points, you know, to a very large scale of new physics. On the other hand, there are other arguments that is telling you that we should expect new physics at a rather light scale. I mean, at a scale that should have already been probed, actually. Right? I mean, the fact, for instance, that CP violation doesn't the strong interactions, QCD, doesn't break CP, right? I mean, if you write the standard model Lagrangian, there is only one operator involving gluons that could break CP, which is a famous theta term, using the field strength of the gluon. And this theta term is smaller than 10 to minus 10, as you know from the measurement of the electron dipole moment, right? So this is a mystery, why CP, why the strong interaction doesn't break CP. And one argument is actually this theta term actually is driven to 0 dynamically by a new interaction, a new field, you know, which is called the axion, is making sure that this theta term is actually dynamical quantity, and the minimum of this axion potential actually ensures that the theta should be very small, close to 0, right? So that's one argument. You should expect to see, you know, in physics beyond the standard model, you should expect to see an axion, which means a particle which is very light and very weakly coupled. Right? Furthermore, also the fact that the weak scale, I mean, the mass of the Higgs boson is much lighter than the mass of any UV scale. I mean, maybe the scale of ground unification or the Planck mass, right? While in principle, if you have an elementary scalar field, you know, you can compute radiative correction, and then the radiative correction of the Higgs mass will drive the weak scale up to the larger scale that you have in your theory, right? So it's really something which is unstable to have a weak scale which is much lighter than any UV scale, provided that the X is an elementary scalar field. Right? So you really need to add new physics to stabilize and to cancel those radiative corrections. So clearly there is a tension, and it's fair to say at the moment that we don't really know where the new physics will appear. I mean, we still hope to discover new physics at Collider, at the LHE, but we should take into account that, you know, there haven't been any evidence of this new physics, so you should really arrange the new physics somehow to be elusive, and there are various ways to do that. I mean, for instance, you can really introduce new physics, you know, in a compressed way. I mean, the fact that, you know, you have new particle with very small mass difference in such a way that you don't really produce clear, I mean, a lot of very energetic jet, for instance, that will be used to tag your new physics, right? Or maybe new physics will actually produce displaced vertices that are harder to search for, you know, at Atlas and CMS, right? Or maybe, you know, new physics doesn't produce any transverse missing energy, right? Which is one element that you really want to trigger on in order to distinguish signal from the background, right? Or maybe new physics, you know, doesn't couple to QCD. And since LHE is really essentially a QCD machine, means that it's very difficult to produce this new physics, right? So there are various model of physics beyond the standard model that really predict this kind of signature. You know, for instance, R parity supersymmetric, R parity violating supersymmetric scenarios, or models that are called twin X or neutral naturalness, really where the new physics, you know, is totally neutral under QCD or even neutral under QED, right? And there are also the model of relaxation that I will be talking about in a moment, right? So what is the connection with the hierarchy problem? You know, really with the connection with the X mass, you want to ensure that the weak scale is stable, right? So it's not sensitive to large quantum correction, not sensitive to large radiative correction to loops effect, right? So there are various approaches. I mean, maybe, you know, you can think of a conspiracy or intelligent design. I mean, you might introduce new physics, you know, to solve the problem of matter-antimatter asymmetry, or to solve dark matter, whatever. So you have new physics, which is heavy, but this new physics has very tiny coupling to the standard model, very tiny coupling to the Higgs field, right? So this will explain why the radiative correction to the Higgs mass is very small. And nonetheless, this is a challenge, right? Because you can always close loops of these new particles, and you know, you can couple this new particle to gluon, to graviton, and this graviton can be off-shell. You know, on off-shell, the graviton coupling can be arbitrarily large. I mean, they can be of order 1. They won't be suppressed by the max, but the Planck scale any longer. So those loop of graviton off-shell can actually produce a large contribution to the Higgs mass that you cannot avoid, right? Because the coupling to gravity is universal. So no matter how new physics is coupled to the Higgs, you know, by closing this loop of the graviton off-shell, you will actually produce a coupling, a correction to the Higgs mass that you cannot rid of. And usually this is a big challenge, right? You will really need to modify the structure of gravity at the Planck scale if you want to get rid of these new contributions, right? So I would say that this is not really an alternative, a viable alternative, right? This is a big challenge that will force us to really discover a new structure of gravity at the Planck scale. The other approach to the hierarchy problem is simply the entropic selection in multiverse, right? It's just telling you that, you know, the electric vacuum that we are living in is actually not unique. There is thousands of 10 to the 300 vacua that exist. Maybe those vacua are created actually by the many D-brane that exist in string theory. So really the building block of matters are not particles any longer, but they are strings or D-brane. And those D-brane will all the flux actually produce all these different and non-equivalent vacua. And out of these different vacua, there is one that looks like our universe, simply because this is the only universe into which basically matter can develop as we know it, right? Matter as we know it, and then giving rise to intelligent observer like physicists, right? So that's one possibility, and just an accident, right? I mean, the universe and the Higgs is light simply by accident. And finally, there is a more conservative approach, I mean, simply a dynamical screening, which means that there is new physics that is there to stabilize actually the electric vacuum, right? So this new physics could be new space-time symmetry. I mean, the prime example is supersymmetry, for instance. Or it could be new forces, new particle. I mean, maybe at the end of the day, the Higgs is not an elementary scalar field, but it's just a composite bound state of a new strongly interacting series, right? Exactly like the same way that the pion, you know, the pion is a light scalar field that emerge from QCD, right? So exactly the same thing. The Higgs could be a composite particle emerging from a new strongly interacting theory. And in this case, you know, the quantum correction to the mass of the Higgs will be screened by the compositeness scale of the Higgs, right? So above a few TeV, then there is no divergences any longer. And the mass of the pion is of the order of the QCD scale. So the weak scale will be of the order of the compositeness scale of this new strongly interacting theory, right? And finally, maybe there is also a new vacua with a dynamical selection of the electric vacuum among these different vacua, right? So let's see, right? I mean, there are several theories. I mean, the traditional model of physics beyond the standard model actually involves a single vacuum. And this is a case of, for instance, supersymmetry or Peche-Quinn symmetry, right? You have really a symmetry that ensures that there is a cancellation of all the radiative correction to the Higgs mass. Or it could be a form factor, like, as I said, in composite Higgs, right? I mean, the radiative correction is screened by a form factor due to the fact that the Higgs is a composite particle. Or maybe you are solving, you know, the hierarchy problem simply by lowering the scale of fundamental physics. You know, the Planck scale is not 10 to the 19 GeV, but it can be much lower. For instance, if there is extra dimensions, and the scale, the size of the gravity, the coupling of gravity is really weak because the strength of gravity is diluted into a very large volume occupied by those extra dimensions. Right? So in that case, I mean, in all these scenarios, basically, you are really expecting new physics to occur around the TeV scale to produce and to cancel those radiative correction. The problem is that all these scenarios have been searched for at the LHE and the previous machine, and they are getting very much constrained already, right? I mean, for instance, the CZ searches, I mean, has excluded the gluino below 2 TeV or 3 TeV, right? And it has excluded some neutralinos also below 1 TeV, right? So basically those constraints, those experimental constraints, basically bring the model into already fine-tuned region, right? You still need, I mean, maybe there is new physics, and this new physics cancel, you know, the contribution to the radiative correction to the X mass, but this cancellation, you know, is not perfect. I mean, there is a tuning, a spatial arrangement, delicate cancellation among various contributions, right? Of course, doesn't mean that, you know, those scenarios are excluded by say, but I mean, you will need an additional structure really to ensure a full naturalness in these scenarios. Or maybe this new structure, you know, could be a form, I mean, a different structure. For instance, I mean, I don't know, this new physics, I mean, the new particle that will cancel the loop of the top quark could be, for instance, particles that are not charged under QCD, right? So these are all the models of naturalness, like in twin X model, right? So, I mean, contrary to the stop in supersymmetry, the stop in supersymmetry is a particle which is charged under QCD. So that's why the production cross-section of the stop at LHE is rather large. But if, you know, the top partners are not charged under QCD, then the production cross-section at the LHE will be much smaller. And that's why we haven't observed them, right? So on the other hand, I mean, those scenarios usually comes, you know, with, I mean, exotic signature. I mean, maybe with displaced vertices, because at the end of the day, those new particles will be weakly coupled to the standard model degrees of freedom. Yeah? So, you know, you will need some time to produce them, right? So they will lead to displaced vertices signature, or maybe you will see some emerging jets appearing. You know, you have an event and then you have invisible particle, and suddenly those invisible particles decay back into the standard models, right? So there is very interesting model building activities, you know, and finally this last piece that was missing, you know, with scalar top partners that don't carry any charge under any standard model gauge group, you know, have been filled out recently. These are the hyperbolic X model or whatever, I mean, top partners that are singlet under standard models, right? So that was one type of solution of physics beyond the standard model with a single vacua. And then there are other type of model that involve multiple vacua and a dynamical selection among all these vacua. So dynamical selection mostly due to cosmological evolution of the universe, right? So this is a case of n-naturalness model, for instance. I mean, you know, there are various vacua that exist, but only the vacua in which the X wave takes a particular value, you know, correspond to the one that we live in. I mean, as a, you know, if the X wave is too small or too large, I mean, this bubble will expand, you know, and then you won't have any possible particle reacting. So you will have empty bubbles, you know, so certainly something that doesn't correspond to our universe, or, you know, those bubbles will shrink much too fast, and then no matter can emerge, right? So it's only the bubbles in which the X wave has a right value that can lead actually to the universe as we know it, right? There are other models like the relaxion, for instance, you know, so there are various vacua, and the X is exploring actually, the cosmological universe is exploring all these vacua. But then, you know, when the X takes its particular value close to the one that we know, you know, there is a back reaction that stops the evolution of the universe. So it stops the exploration of these vacua, of these different vacua. So we really live in a vacua with X wave that is close to the one that have been measured. So those kind of models, you know, with an interplay between cosmology and particle physics has led actually to a paradigm shift, right? Because all the previous model that I was discussing before, you know, was really predicting a new physics at the TeV scale. But now here, and in all this model of cosmological evolution, actually you expect new light degrees of freedom, new light physics, which is very weakly coupled to the standard model particles, right? To the standard model degrees of freedom. So this means that to test, I mean, those kind of model, those model, LHE or the energy frontier, so maybe FCC, whatever, all these colliders that I've been discussing before, are maybe not the best place to actually probe those kind of models, right? And you will need to actually look at various other type of experiment to really be able to search for these light degrees of freedom. So it could be, for instance, doing some astroparticle measurement, looking at dark matter halos or superradiance, allow you to probe really some light new particles with a mass, let's say, around or even below electron volt. Or maybe you will do some precision frontier, coming from precision measurement in atomic physics, to really be probing something like masses of the order of 10 to minus 10 electron volt, right? So really there have been a log crisis in Higgs physics when you really try to explore those various energy domain, that are not the one that are traditionally explored, let's say, at colliders, right? And indeed, there is some connection, let's say, with intensity frontier. So maybe, one best probe of physics beyond the standard model is actually the measurement of electric dipole moments, of the electron, for instance. You know that in the standard model, there is a prediction of this EDM of the electron, which is very tiny, due to the CKM suppression, for instance. So you need at least to involve the 3 loops, 3 or 4 loops, to be sensitive to CP violation within the standard model. And this turns out that, the EDM of the electron is very tiny, something like 10 to minus 40 times E, the electric charge per centimeter, right? And we are not yet there. Experimentally, we are not sensitive to this EDM, right? At the moment, there is, fantastic experimental progress. We are reaching something like 10 to minus 29, 10 to minus 28. There is this famous ACME experiment a few years ago that improved by more than 1 order of magnitude these EDM bounds, right? And really these EDM bounds, could be a fantastic probe of a new source of CP violation in physics beyond the standard model, right? Really the dramatic improvement in the experimental sensitivity really put dramatic bound on CP violation in physics beyond the standard model. And there is really fantastic new ideas. For instance, there have been the idea of measuring EDMs, using polyatomic molecules, right? And there you will also improve the experimental constraint by several order of magnitude, right? So this is really something that you should keep an eye on, really, because this will give some very strong bound on physics beyond the standard model. And then you can use this bound from EDM, for instance, to put some bound on new state of physics beyond the standard model that you expect. For instance, in composite model, as I say, you expect new partners of the top quark to cancel those radiative correction, right? And here you can see, really, you can compare the bound coming from the ACME EDM measurement in black in this line, compared to the direct searches, for instance, at the LHE or high luminosity LHE or FCC HH. And you see that really these EDM bonds will give, indirect, but they will give unbeatable constraint on the masses of these new particles. Right? Similarly, there is also very interesting constraint of physics beyond the standard model, looking at lepton flavor violation. The previous speaker already talked about that, but really there is some dramatic improvement that you can expect, for instance, in measurement of muon into free electron or muon into electron and photon, right? So these are, again, processes that are highly suppressed in the standard model, but they will be, possibly enhanced dramatically in physics beyond standard model, either by a Z prime or either by a loop of neutralino in supersymmetry. Really, those processes will give us the best constraint on physics beyond the standard model, for instance, that satisfied a minimal flavor violation on that, in order to get rid of all the constraints that are coming from delta F and delta F equal 2 or delta F equal 1 flavor data, right? And finally, you could also put some bounds on physics beyond the standard model, on this new very light degrees of freedom, looking at atomic physics. For instance, you look at particular atomic transition, an atomic transition inside some particular atom, and you would like to see how those atomic transition change when among different isotopes, right? So if you have only, let's say, QED, then you expect that this isotope shift will be aligned. Actually, this is a famous result in atomic physics. This is called the King linear plot. And then if you have new physics, beyond QEDs, then you expect actually a departure from this linearity, right? So the question is actually how how accurate you can be in the measurement of this atomic transition. And there have been fantastic progress already in atomic physics, you know, with the sensitivity now reaching the level of 10 to minus 18 really in this measurement of atomic shift. And you can see really continuous progress. I mean, for instance, last spring, there were measurement of ytterbium ion King linearly plot at the level of 300 Hertz, and then using calcium you can reach 20 Hertz, and you can see that here you will really be competing now with constraint on, you know, these light degrees of freedom that are much better than the measurement from phi4 for globular cluster G-2. Right? You can really get very interesting constraint on physics beyond the standard model using atomic physics. Right? Okay, so I have only 2 minutes left. I mean, to tell you about new physics in the dark sector, you know, that could be responsible for dark sector. And here again, I mean, thinking of WIMP, I mean, there are, I mean, WIMP or very light WIMP, I mean, dark matter that are in thermal equilibrium. You know, there is a fantastic new possibility of measuring and putting constraint on these scenarios, not only using nuclear recores that are very efficient, you know, for heavy WIMP dark matter, but for light dark matter and thermal dark matter, it's better actually to use and exploit the electron recores, you know, where you will be sensitive to much lighter mediator of dark matter, right? And there have been, again, fantastic experimental progress on this side. I mean, using atomic ionization, like in xenon experiment, or using semiconductor, like in the Sensei experiment. And then again, using superconductor, dark matter scatters on Cooper pairs and breaks the Cooper pairs, etc. Did give you a fantastic new way to really probe these light dark matters. And these really are exploring very interesting scenarios of dark sector. There are other experiments in the intensity frontier that are also searching for light weakly coupled sectors that belong to the dark sector, like for instance, axion-like particle. You know, you can look at mixing of these ALPS with the standard model meson, and for instance, look at exotic decays of the K-on, K-long, or K+, you know, that will decays into pion and an axion, and then will decay back into 2 photons, right? And here you can see really the sensitivity on the mass of this axion and on the axion decay constant, right? I mean, this is very fantastic new constraint on this ALPS scenario. You could also probe the ALPS directly at collider, like for instance, producing an axion with a Z or with a Higgs boson, and you are probing actually in this case, new type of interaction, a new type of coupling of the axion, let's say, to the standard model gauge boson, to the Z or the W or the Higgs boson, right? There are also nice measurement coming from beam dump experiment, you know, like the SHIP of the dark quest experiment that will be probing in particular the dark photon scenarios. And finally, you shouldn't forget also that, I mean, the X factories, I mean, in particular, the circular X factories will be actually Z factories. They will produce something like 10 to the 12 Z's. You know? Six order of magnitude more Z will be produced at this FCC-EE than compared to what was produced at LEP. And you can use actually this Z, you know, to produce actually bottom quark or produce tau quarks. And then you can really perform a fantastic flavor program using this X factory. Actually, if you look at the rate, you will produce more K-on or taus at this FCC-EE than you are producing at Bell 2 or LHCb, right? So these are really the new flavor factories that will be used to probe physics beyond the standard model. Okay, so my time is over, so I cannot talk about gravitational wave and how to probe new physics using gravitational wave. I will just conclude very quickly. I mean, we don't know. I mean, it's fair to say that we don't know what physics beyond the standard model is, for the simple reason that if we were known, you know, it will be part of the standard model itself. Nonetheless, I mean, we haven't discovered any physics beyond the standard model, but we know that physics beyond the standard model exists. So we should keep searching, because looking and not finding is very different than not looking at all. And there is a very vigorous experimental program on a vast range of energy scale, and it will surely guide us to a new understanding of nature, right? And the X Factory program, you know, which is the main driver, is also complementarity with a very diverse program, you know, with beam dump experiment, with, I mean, atomic physics program, and we will really be enjoying life for the future, right? And probably now understanding what will come after the standard model. So we'll stop here. Thanks a lot.
Thank you,
So-
Christophe. Thank you. Questions for Christophe?
It's probably getting already
Okay.
quite late in India, right?
Diptimoy, please go ahead.
Yeah. So, hi, Christophe. How are you?
Hello.
Hello. So, yeah. So, I wanted to ask you whether, other than the hierarchy problem,
Yes.
is there any problem which does not have a UV solution? Naively, it seems like no, but what do you think?
Well, I mean, I don't know. Dark matter doesn't really need a UV solution, right?
No,
It can be some-
need is a different question. Need, if you say need, of course, many things don't need to have a UV solution. But is there anything which doesn't have, other than hierarchy problem, a UV solution? It seems to me that everything has a UV solution. So it's you see that these days I'm probably very depressed because of COVID. So so that is why I'm asking this. So
I don't know, confinement. I mean, confinement is in principle an infrared problem, right? I mean, it's
no, that is an infrared problem. But I'm saying, in terms of BSM or the problems in the standard model and the ones you described, for example.
Well, I think, I mean, strong CP, strong
CP is really... strong CP. That I had mine, but I'm considering it as a UV solution, which has a very IR, effect.
Okay, Pechequin symmetries, and okay, if you think of a Pechequin origin of the axon, yes, but I mean, the axon doesn't really need a Pechequin origin, right, in principle.
So I'm just saying, in principle, this is a kind of a nightmare scenario, but in principle, if I forget about the hierarchy problem, every other thing, baryon asymmetry, a CP, it seems like everything in principle can have a very UV solution. And then if you are not lucky, you won't see anything anytime in our lifetime.
Diptimoy, let Christophe answer, and then you can take offline. Okay?
No, I mean, we don't know. I mean, it's clear that, I mean, it could be that new physics really push to very high scale, that the solution of all our problems live in the far UV, where you will have no direct evidence, at colliders. In that case, I mean, maybe the best way is actually to look at cosmology, because cosmology has been exploring, really some UV scales, right? So you need to find imprints of this UV history inside cosmological data, right? And for that, I mean, gravitational wave is certainly giving you a nice imprint, right? I didn't have time to cover this part of the talk, but I mean, look at that. I mean, you can use, for instance, gravitational waves that are produced by a cosmic string. You need to really be sensitive to a very large time, a very large time in the cosmological history of the universe, right? So yes, in that case, I mean, I think cosmology will be the best way to probe this UV solution of our problems. Right?
Okay. Next, Sanjay Kumar Swain, please.
Yeah. So it's just a statement. Maybe you can make a comment on it. So in the previous talk, unlike in clever physics, we had a K-pi anomaly or RD star tension between standard model and data. I think in Higgs sector, there has not been any problem between standard model prediction and the experimental data so far. And secondly, this hierarchy that Diptimoy showed, I don't think it's a problem. It's more of a conceptual problem rather than a problem like unitarity or something, right?
Okay, I mean, yes, it's not, I mean, the hierarchy problem is not an inconsistency, right? I mean, that's contrary to unitarity. It's more like, I mean, the black bound, I mean, the bound of our understanding of effective field theory, right? I mean, in the sense, if you consider the standard model as the ultimate theory valid up to arbitrary high scale, then clearly there is no hierarchy problem. And to have a hierarchy problem, you need at least two scales, right? So then, I mean, the hierarchy problem is to really understand how the weak scale is totally insensitive to the detail of the physics in the UV, right? So it's really a decoupling problem. Right?
Yeah.
And yes, so in order you want to be able to make some prediction that are very robust and insensitive to the details of what is happening at scale that you will have never access to directly, right? Yeah, so you are right that, I mean, in the sense that in X physics, there is no discrepancy compared to the prediction of the standard model. I mean, for the simple reason that, the X measurements are not sensitive enough yet, right? I mean, in the sense that flavor data that you were talking about, measurement that are a precision that are of the order of per mil, right? And X physics at the moment is more like 10%, right? So it's fair that we didn't see any discrepancy in X physics. Well, you see some anomalies, let's say, in flavor physics.
I agree.
Okay. The last question, Somen.
Yeah, slight outsider to the field. You mentioned about this first order electric phase transition and bubbles formation. What will be a possible direct experimental signature that you would like, most promising experimental signature for directly asking whether the phase transition is first order or not?
Well, if you ask a direct experimental evidence, then you would like to see the dynamics of the phase transition. So that's something that you will never be able to reproduce in collider. So for that, you really need to look at cosmology again, to find some leftover of this phase transition. And one clear signature, will be, for instance, the production of gravitational wave, because you produce bubbles, those bubble collide, or there is some non-trivial plasma effect associated to this bubble, and this will produce gravitational wave with the characteristic spectrum, with a peak which is related to the size of the bubble at the time of the phase transition. So for first order phase transition occurring at, let's say, 100 GeV, you expect nowadays, gravitational wave that you will see today after the redshift, you will see a spectrum which is peak around millihertz, like 10 to minus 3 hertz, right? So much lower than the, frequency much lower than the gravitational wave observed at LIGO, right? But there are some gravitational wave detector like LISA, that will be sent in space in few years, that will be really, peak with a peak sensitivity around this millihertz frequency. So they will be the best detector to really be sensitive to a first order phase transition around the weak scale.
So that should be able to rule it out. Kind of definitive statement about the order range.
Definitive statement, not totally, because clearly, there is the dynamics of the phase transition, but you need also, know the amount of energy which is.
Yeah. Let's say a strong.
You need to know the amount of energy which is released, right? So not only there is a frequency, but there is the height of the peak, right? And the height of the peak will be below the sensitivity of LISA, right? So it depends on two parameters. You will constrain, large parameter space, but you cannot totally exclude that there is a first order phase transition that release not enough, energy to leave some visible signature, right, in gravitational wave detectors.
Thank you.
Thank you. Thank you, Christophe. Thank you for a very good talk. And thank you for spending time with us. Thank you.
Thank you very much. Bye-bye.
Bye-bye. So the next speaker, Greg, can you share it? So the next speaker is Professor Greg Landsberg, Thomas J. Watson Senior Professor of Physics from Brown University. I have known Greg since 1992. Greg, we don't need to introduce too many in the crowd. Greg is an excellent experimentalist. He has led the D0 Exotica and New Phenomena Group, Deputy Physics Coordinator of CMS. He has led many physics group, and his letters towards the B physics. But we know that he has also was the physics coordinator. He has led CMS Exotica and other things. So Greg Landsberg, good morning, and thank you for getting up early in the morning for us. So, Greg.
Thank you for this kind invitation. Let's see. Do you see the full screen mode?
Yes, Greg. We see the full screen mode.
Great, excellent. So thanks a lot for the kind invitation, Zoom invitation rather. It's a pleasure to be here. And what you see on my first slide is the most famous beach in the world since this year. This is a bit allegoric to what Christophe was talking about, because no one really knows where this beach is and whether it even exists. So it's a good allegory to BSM physics, but we all know about it and love it. So with that, let's go to the main part of my talk, and I will start with the LHC legacy. The run 2 was a big success. We have about 160 inverse femtobarn delivered by the machine at 13 TeV. This exceeds the original integrated luminosity projections. And about 140 inverse femtobarn of physics quality data has been recorded by each atlas and CMS. So thank you, LHC, for a spectacular run 2. And we look forward for a even more spectacular run 3. I think it's important to notice that LHC is not just one machine. In fact, I would argue that LHC is 3 machines in one. And Valerie already told you about one of these machines. LHC is the B factory. But LHC has figuratively replaced 3 machines in one go. The Tevatron in terms of high PT physics, standard model physics, and searches. Bobar and Bell B factories in precision B physics, and Rick in heavy ion physics. The LHC experiments in general and Atlas and CMS in particular are very successful in all of these 3 areas. We just heard excellent talk from Valerie about the B physics, and I'll talk a little bit about the other stuff. And of course, this wouldn't be possible without theoretical and phenomenological breakthroughs of the past decade. Christophe didn't talk about those because they are more of the standard model things, but higher order calculations, the so-called NLO and now NNLO revolution, modern Monte Carlo generators, and reduced and better estimated PDF uncertainties are crucial components of our ability to do standard model measurements and searches. Since it's impossible to cover all the aspects of this impressive program in a single talk, I'll focus on a few recent highlights from Atlas and CMS in Higgs physics, standard model physics, flavor physics, heavy ion physics, and the discovery program. And the choice of topics clearly reflects my personal bias in what have been the most significant achievements of the past year. And of course, if you're interested in more, each Atlas and CMS by now submitted close to 1,000 papers based on collision data. That's about 100 a year. And this is plot from CMS. You see most of these papers are on searches. This is exotic and SUSY searches in green. And a similar situation is in Atlas. So let me start with heavy ion highlights. I want to show you just 2 results, one from Atlas and one from CMS. And I would like to start with light by light scattering. This is a sizable correction for many precision measurements, most importantly, G-2 theoretical prediction. So it's important to measure light by light scattering experimentally and compare with theory calculations. Now, heavy ion running essentially turns the LHC into a photon-photon collider. So I would argue that we have 4 machines in one. Photon-photon colliders do not exist yet, but the LHC is a photon-photon collider in a certain mode. And you see that one could study light by light scattering via this box diagram through the enormous flux of photons emitted by colliding nuclei. For low Q-square processes such as light by light scattering, the flux of photon from each nucleus is coherently enhanced by Z squared because it's the nucleus itself which emits photon, not individual protons inside the nucleus or individual quarks. And therefore, the flux per lead nucleus is enhanced by Z squared. And the overall enhancement is Z to the 4th, which is 50 million for lead-lead collisions. And therefore, LBL scattering has been measured by both Atlas and CMS successfully. And what I want to show you is the new analysis from Atlas, which provides the first measurement of this phenomenon differentially. So the main background to light by light scattering are production of E plus and minus pairs, which you misreconstruct as photons, as well as exclusive central production in gluon-gluon interaction. The former background is estimated fully from data, and the latter is estimated by a simulation, which is normalized to the control region of large aplanarity of the diphoton system. The signal itself should have very low value of aplanarity, but you see that the central exclusive production and also the E plus and minus background go up to very large values of aplanarity, which allows you to constrain them in the feed. And as a result, you see this very nice differential spectra in the diphoton mass, diphoton rapidity, sum of the photon PTs, and cosine of the scattering angle in the center of mass frame. They reasonably agree with the theoretical predictions, although while experimental uncertainties are still large, there's about 1.5 sigma over measurement compared to the theoretical prediction. Whether it's real or not remains to be seen. Now, these very same results could be used to also set limits on axion-like particle, ALPS, decaying to diphotons by looking for narrow peaks in this M-gamma-gamma distribution. And if you do this analysis, the limits set in this Atlas paper are shown in dark blue on this diagram. You see that they extend on the left limits and previous limits from light by light set by CMS. So it's a very nice result, which probes, 10 TeV scale, roughly similar to what Christophe was talking about. The other interesting measurement in heavy ion physics is the first evidence for top quark production by CMS. This is a very rare process in lead-lead collisions. And in this analysis, we explore dilepton decay channel with or without B-tag jet requirement. The main results of this analysis actually come from the untagged channel, because in the heavy ion environment, there are jet quenching effects. And the jet quenching actually affects the big quark jet potentially different from light jets. And this has only been measured by one experiment so far. So the uncertainties on the B-jet quenching are rather large. So for that matter, you are doing better by doing this, the measurement in the non-B-tag channel, where you don't rely on the jet at all and only look at the dilepton system. And if you do so, you basically measure the cross-section, which is in a good agreement with theoretical prediction. You could also compare it with the proton-proton reference at the same center of mass energy, scaled to the number of participants in AA collisions. And this analysis is the first evidence for the top quark pair production in lead-lead collision, with the observed significance of 3.8 and expected significance of nearly 5 standard deviation. Since Valerie covered the B physics very precisely and showed a lot of results, I will just show one result from CMS, which was on one of her summary slides. And this is the measurement of CP violation parameters in the B sub S to J psi phi process. This is a classical process. The new CMS measurement takes advantage of the opposite side muon tagger based on deep neural networks. And the 3 muon trigger, which uses the 2 muons to trigger on J psi and 1 trigger on the opposite side to ensure a semi-leptonic decay of the other B produced in the events, because B's are produced in pairs at the LHC. And that combination of the better tagger and the special trigger allowed CMS to enhance the tagging power, epsilon d squared, to about 10%, which is 10 times better than what we had in round 1. The analysis based on 2017 and 2018 data, because this trigger was not available in 2016, and it's based on full time dependent angular analysis in 3 angles shown in this picture. The tagger was calibrated in the self-tagging B plus minus to J psi K plus minus decays. And you see that it shows excellent linearity in terms of taggability. And that allowed us to measure fairly precisely the parameters of the standard model, particularly the ones which depend on the B tagging, or look for non-standard model contributions to CP violation. Here are all the parameters measured with their uncertainties, which are still dominated by statistical uncertainties in most of the cases. And the new result is shown here. You see that precision on phi S is more than a factor of 2 better than precision obtained in 8 TeV analysis because of the combination of better tagger and the better trigger. We now probe the standard model with quite nice precision. The theoretical uncertainties in the delta gamma sub S are similar to the experimental uncertainties now. And Valerie showed you how these results agrees with the LHCb and other results, which also prefer the standard model. So unfortunately, we don't see any deviation from the standard model, but still there might be surprises in phi S, which is predicted incredibly precisely, but the uncertainty in the measurement is still around 50 millirad. With that, let me move to the standard model highlights. And one important highlight are the tests of lepton universality. There has been a long-standing puzzle in the field since lab era, namely the W to tau nu branching fraction was measured consistently higher in all 4 lab experiments compared to W to E nu or W to mu nu branching fractions. And the combined result, R tau mu, is nearly 3 sigma away from unity. And for almost over 20 years, this has been dominated by the lab precision. So is this a possible hint of lepton non-universality or a statistical fluctuation? Well, the new analysis of ATLAS seems to address this question and settle it once and for all. It based on large samples of muonic W decays in TT-bar events, either prompt or via tau lepton. And this enormous number of top quark decays, LHC is clearly a top factory, made it possible for precision test of the lab result. So the idea is to tag one top quark by its lepton utilizing the probe muon PT and its impact parameter with respect to the vertex to distinguish prompt and non-prompt events. Since taus have a rather significant lifetime, muons are less pointing in the tau decays than the prompt muon, as you see from this plot. And with large sample of the TT-bar event, essentially
Hello.
Yes, Vedang, we can hear you.
Yeah, Vedang, I was thinking that it is my internet, but it looks like Greg is...
No, it's something, there's some glitch on my side.
Oh, okay, no problem, Greg. Welcome back.
I apologize for that.
No problem.
So let me switch back to the talk. I just need to find it. That's the disadvantage of the virtual meetings. Never happened to me in real life. Okay, do you see this? No, you don't see the slides.
No, we don't yet. Yeah, you have to share.
So let me share again.
Sure.
So I share, and now you should see these slides, right?
Searches for LFT. Yeah.
Terrific. Let's hope won't be interrupted anymore. So related topic are searches of lepton flavor violation in various sectors, which is particularly topical due to the flavor anomalies you heard about from the last 2 talks. And by now, each ATLAS and CMS has 2.5 orders of magnitude bigger samples of Z boson, at least produced, than all 4 lab experiments together. We have about 10 to the 10 Z's per experiment, whereas the entire statistical lab is only 20 million. So it's possible to explore lepton flavor violation in Z boson decays with unprecedented precision, particularly for the lepton flavor violating couplings involving 3rd generation leptons. Previous best limits on the tau E and tau mu decays of the Z were set by lab at about 10 to the minus 5 for unpolarized tau leptons. And the challenging new ATLAS search for the Z to tau E and tau mu using hadronic tau decay for the first time allowed us to actually improve on this precision. So the search explores signature with an isolated energetic lepton, electron or a muon, and a tau-like jet, which could be either single prong or three prong, with relatively small invariant transverse mass and rather large visible mass of the tau and lepton. And you see from these plots, which show you the transverse mass versus visible mass, that signal occupies low transverse mass and rather large visible masses. So that's the area where we focus, which allows us to reduce the other dominant backgrounds from the tau-tau decay of the Z and the W plus jets. And the rest of the backgrounds actually are reduced via dedicated neural net. And these are the new limits at 95% confidence level for unpolarized taus on these lepton flavor violating decays. And you see that they exceed for the first time lep limits. So by the way, there's a slight excess, but only about 1 sigma seen in this analysis. That's why the expected limit on tau mu is actually much better, 50% better than the observed one. The other important topic of the standard model is vector boson scattering, because this is an ultimate standard model measurement to be done at the LHC, since we need to experimentally verify the unitarization of the scattering amplitudes due to the exchange of the Higgs boson. With run 2 data, we finally reached the sensitivity to observe first VBS processes, such as electroweak WW production, including the same sign W production, electroweak WZ production. And in this talk, I will show you 2 new results on electroweak production of W gamma and ZZ. Let me start with the W gamma, which is the new CMS analysis. We look for production of the W gamma system in association with a pair of forward jets with large rapidity difference. These are the electric diagrams we would like to probe. And these are the QCD diagrams, which are background to these processes. So we are sensitive to both quartic couplings via this diagram and also vector boson scattering diagram. We need to separate this process from the QCD backgrounds, which is done via a control region with relatively small diejet invariant mass, which emphasizes this diagram. And signal is extracted from simultaneous feed to MJJ and lepton gamma distribution. The signal strength measured in this analysis is 1.2 with about 25% uncertainties, which corresponds to 4.9 absorbed signal significance. And with combination of with 8 TV data, the significance is pushed above 5 sigma. So this is the first observation of the electroweak W production, and the measurement of its cross-section and also cross-section of the sum of QCD and electroweak production are consistent with the standard model. You could also set a strict limit on anomalous quartic gauge couplings shown in this table. Our friends across the ring just published observation of the first electroweak ZZ production. This is the production of ZZ system in association with a pair of forward jets, again, sensitive to the quartic diagram, and the background comes from this type of processes. The 4-lepton channel is virtually background free, but they also looked at 2-lepton 2 neutrino channel, where the main backgrounds are TT bar and WZ production. The QCD contribution was estimated via control regions and suppressed by a multivariate discriminant. And the combined significance in these 2 channels reaches 5.5 sigma with 4.3 expected. They were a bit lucky of seeing slightly more event, which corresponds to this measured fiducial cross-section, which is slightly higher by about 1 sigma than theoretical prediction. So excellent measurement and first evidence, first observation actually of electroweak ZZ production. In fact, LHC dazzles us with its precision. Just to show you the plots from Atlas and CMS, which were christened as Stairway to Heaven, where you see this ladder of measurements which span some 14 orders of magnitude in cross-section, from jet inclusive production all the way to various processes such as quartic couplings, the production of 3 vector bosons, the ones which I talked about, and similar plot from CMS focuses on the production of various particles in association with top quark or top quark pair, probing cross sections of the order of 1 to 10 femtobar. Quite impressive. You might ask yourself why it's called Stairway to Heaven, and this ladder leads down rather than to the sky, but this is easy to fix with modern tools. So now it is Stairway to Heaven. So let me move to top physics highlights. And one very important measurement which was done recently is moving us closer to the measurement of the 4-top quark production. This is a very rare process in the standard model. The expected cross-section is only about 12 femtobarn, but it can be significantly enhanced in a number of new physics models. For example, SUSY scenarios where gluinos decay into top and stop decays into top quark and neutralino. So this gives you 4 top quarks in the final state. And after several publications just setting limits on this important process, we finally have the first evidence for observing it. Despite the smaller branching fraction, the most sensitive search is in the 3-lepton and also 2 same-sign lepton channels, which have vanishing standard model backgrounds. So Atlas just published the first evidence for this production using this channel with at least 2 BTAC jets based on full run-2 data. The main irreducible background come from production of various bosons, including Higgs with TT bar. This is first time, or one of the first time, when Higgs boson actually becomes the background rather than the new particle in just 8 years. And TTW, which is corrected using control region and data. Smaller reducible backgrounds are estimated from data, and analysis sensitivity is maximized by a boosted decision tree, which explores the presence of BTAC jets and kinematic properties of signal events. And you see quite clearly the signal in dark red in the enhanced BDT spectrum. This is the sum of the BTAC scores of all the jets. You produce a lot of B jets in 4 top events. And this BDT actually has the BTAC as one of the important parameters. So you clearly see very large excess of the events from the standard model backgrounds. And that allows Atlas to measure mu, which is actually quite high. It's about 2 sigma beyond the theoretical expectation, well, a little less than 2 sigma. And they measure the cross-section of 24 plus minus 7 femtobarn, which allows them to claim the observed significance of 4 sigma with expected significance of about 2.4 sigma. So that constitutes the first evidence for top production. At the same time, CMAS did the direct measurement of CKM matrix elements VTS and VTT. You heard from Valerie's talk that these elements can be constrained indirectly by B and K decays, but this is the first model-independent measurement of this matrix element directly using single top quark production, which actually is sensitive to the diagram, which have VTD or VTQ as part of the amplitude. So these diagrams are sensitive to the VTQ squared, in addition to the main diagram, which is proportional to VTB squared. Now, from the indirect measurements, the VTQ is very close to 1, and the limits on VTD are of the order of few percent to 1%, which would correspond to the following branching fractions of top decaying to various quarks. Almost 100% in B, and then 1-2 per mil, and less than 10 to the minus 4 in the S and D quarks. So the analysis explores the full set of contribution to simultaneously extract all 3 matrix elements squared without any model-independent assumption, using the lepton decay channel leading to the lepton plus jet events. So the analysis is categorized in 2 jets, 1 BTAC jets, 3 jets, 1 BTAC jets, and 3 jets, 2 BTAC jet categories, which have different contributions from different diagrams shown here in different cross-section and branching fractions. So if you combine these together and fit all 3 channels simultaneously, you could extract the matrix elements of the CKM matrix. And this was done in 3 different scenarios. One is the standard model scenario, where you assume the unitarity, namely the sum of the squares of all 3 matrix elements equal to 1. And that allows to set the limit on VTB greater than 0.97 and the sum squared of VT D and VTS less than about 6%. And then you could also probe 2 BSM scenario. One removes the unitarity constraints, which would be, say, if there's a forced sequential generation of quarks, too heavy to be seen directly. And in this case, VTB is measured to be 0.9988 with this uncertainty. And the sum of VTD squared plus VTS squared is 0.06 with 100% uncertainty. And the second BSM scenario actually assumes invisible decays of the top quark in the invisible particles. And in this case, one could again constrain these elements to a similar precision and also measure the ratio of the observed width of the top quark to the total width, which is 0.99 with the 40% precision. So this is the first model-independent direct extraction of CKM elements related to the top quark. So now let me move to searches in the last few minutes I have. Let's start with SUSY searches. And there's a very nice analysis which searches for long-lived leptons. This is an extension of standard dilepton analysis for the case of displaced leptons sensitive to long-lived particles. For instance, leptons in GMSB SUSY, which are often degenerate in mass and have a large lifetime. This analysis requires 2 displaced leptons, either electrons or muons, not coming from a common secondary vertex. So single electromagnetic and single muon triggers, which are not sensitive to the displacement within the range of displacement of this search, were used. And offline, a special tracking algorithm sensitive to tracks with large transverse impact parameters up to 30 centimeters was involved. The backgrounds are very low for decays exceeding decay lengths of, say, 3 millimeters, where all the heavy flavors already decayed. So the main backgrounds just residual heavy flavor decays and cosmic rays, which are estimated by control regions in data. And background predictions is very low. 0 events were observed, which allowed Atlas to set very impressive limit on the lepton masses as a function of their lifetime within 10 to the minus 2 to 10 nanoseconds. And these limits by far extend the limits from LEP. Again, this is the case when previous best limits were unchallenged for nearly 25 years, but now they are completely exceeded in all different scenarios. Now, what about heavy SUSY? As mass limits on SUSY particles, particularly the colored ones, are pushed up, further extensions of the sensitivity requires special reconstruction techniques. In particular, decayed products in SUSY chains are highly Lorentz boosted, resulting in the overlapping particles or jets in the final state. And one needs to use jet substructure techniques widely used in other massive resonance searches, but as a rule, not yet in the SUSY analysis. So the results of first searches of this type are now becoming available, and I will cover one of them, which is Chi2 mediated gluino decay in CMS via this diagram, which is known as T5ZZ. You produce 2 Z bosons, which have very high boost if gluinos are heavy. So we required 2 Z bosons reconstructed as large radius jets with substructures, ordinary jets, and missing transverse energy, which significantly reduced the background while retaining most of the signal efficiency. And what you see by comparing plot on the bottom left with this plot, and I could go back and forth, is that requirement of the 2 Z boson reconstructed as this jet in substructure reduces backgrounds quite dramatically and enhances the signal, which allows us to probe gluino masses up to about 1900 GeV in this particular model. Dark matter searches, another very important program of the LHC. And here is a new analysis, which is a new entry in the MONA-X saga of the dark matter searches, where we look for something produced against the recoil, which is dark matter particles. So it's one particle or one set of particles recoiling against missing transverse energy. So we, for this analysis, we actually look for dye-boson production in association with dark matter. And this is the first time this analysis was done. As a benchmark, we use the model with two mediators, Z prime and dark Higgs boson, and dark matter particle, which is usual Dirac fermion. You could ponder how desperate this model is, or ask Christophe what he thinks about this model. But for experimentalists, it doesn't really matter. This is just the benchmark. The important point, and this is a new signature which has never been explored before, so it's worth exploring under the idea of not looking is different from looking and not finding, as Christophe told you in his conclusion slides. So dark scalar decays to a pair of W and Z boson, just like regular Higgs. And that's how you could look for pairs of W and Z bosons recoiling against the dark matter particles. So the analysis uses a new techniques in Atlas, which is so-called track-assisted reclustering, TAR technique, which is similar to particle flow used in CMS. Subjet information is improved using track-based quantities, such as mass and subcluster observables, which have higher precision, and TAR jet with either four-pronged substructure or one TAR jet and two smaller radius jets are signature for this decay of two vector boson in four quarks. Backgrounds are dominated by Z plus jets and W plus jets production, and they are estimated from control regions in data, and signal is extracted by looking at the mass distribution, which is either TAR jet mass or the mass of the TAR and two regular jets. You see that signal peaks at around 150, and there's no evidence for signal which allows them to set limits on this model, which may be not particularly interesting as limits on the additional scale and additional Z prime, but these are important measurement of a new channel which hasn't been explored experimentally before. And let me cover one exotic search. This is a search for displaced jets, which you would expect in neutral naturalness, as Christophe explained in his talk, for instance, twin Higgs, but you also expect this type of signatures in SUSY models and other models of new physics. Typically, search for displaced jets requires dedicated trigger, as otherwise the rate of inclusive dijet events is simply too high. CMS has invested in several such triggers in Run 2 and achieved superior sensitivity of this type of searches. A typical displaced jet trigger requires a large scalar sum of jet PT, which is called HT, above, say, 400 to 650 GeV, and more than two jets with a cap put on a number of prompt tracks. This offers sensitivity to a large set of models, including models with pair-produced dijet resonances. And the latest CMS search based on 2017 and 18 data is combined with an earlier search using only 2016 data. The main backgrounds are jets produced in nuclear interactions in the pixel detectors. We could in fact map our pixel detector with this type of events. And what's happening is that we exclude these magenta rings from the analysis. So we only require jets to originate where we don't have much material in the detector. And we observed one event in the last bin of the boosted decision tree discriminant with the expected background of around 3/4 of an event, which allows us to set quite impressive limits in a number of models. This is pair production of resonances decaying into a pair of jets as a function of their lifetime and mass. This is Higgs decaying to two scalars, and this is stop pair quark pair production with RPV decays. So a very powerful analysis, which can also be used for other models such as twin Higgs models and so forth. Finally, in the last minute, the Higgs physics highlights. And let me remind you that Higgs actually turned 8 this year, and it's awesome since 2012. Here are some highlights of how Higgs grew over these years. It was born in 2012, first steps 2013. In 2014, we could actually answer the question, what is the Higgs? and it looks like a standard model Higgs. In 2015, we started wondering why Higgs is alone, why there are no other Higgses observed. In 2016, we started exploring Higgs coupled to dark matter. 2017 was trip to the Tau land, and 2018, 2Bs or not to be. 2019 showed the first charm analysis when Higgs is charming. And in 2020, we made a first immunization of the Higgs. So let me show this result about Higgs immunity. The closest we get so far to test Higgs boson couplings to the second generation fermions was by looking at Higgs decaying to a pair of muons. This is an extremely important measurement as it allows to see if there are any non-Higgs mass terms that would undoubtedly require BSM physics and would manifest itself in the mass to Yukawa coupling ratio for relatively light fermions such as muons different from 1. This is tour de force analysis for both ATLAS and CMS, uses state-of-the-art muon identification and momentum correction to achieve the best possible mass resolution, and categorized events according to the production mode and or resolution to use multivariate techniques for suppression of the dominant Brownian background, and of course, full run-2 dataset to maximize the sensitivity. Here is search in ATLAS, which has 20 exclusive categories probing different production mechanisms, with the mass resolution achieved between 2.6 and 3.2 GeV. And the measured signal strength is 1.2 with 50% uncertainty, which corresponds to observed expected significance of 2 and 1.7 sigma. So that's a first hint. And CMS just published the first evidence for Higgs 2 mu, also doing very sophisticated categorization over the different production mechanism and categories with different mass resolution. Fit to the dimuon mass resolution is done in all categories except for VBF, where one fits directly the MVA because statistics is very low for the mass plot to be produced. And if we combine all these categories, we start seeing budding signal for the Higgs boson at the right mass, 125 GeV, with observed and expected significance of 3 sigma and 2.5 sigma respectively. So this is the first evidence for Higgs 2 mu. This analysis was also combined with earlier 7 and 8 TV analysis, which resulted in this ultimate value of mu, 1.2 with 40% precision, and observed significance still 3 sigma, which allows us to put one more point on this straight line showing how different the Higgs is from the standard model prediction. And so far, muons are dead on the money. We don't see any evidence, unfortunately, for non-standard model contributions to the muon mass. So in summary, with LHC doubling time getting similar to a lifetime of a typical PhD student in a large collaboration such as ATLAS and CMS, we now see a gradual shift to more sophisticated analysis than before that take more than 1 year to complete. Those include dedicated techniques, and I showed you a lot of those, dedicated triggers, and sophisticated models and analysis methods. ATLAS and CMS produced a wealth of results in all areas of particle physics, including heavy ion and B physics, thus demonstrating the power of general purpose experiments. I showed you just a very few selected examples which marked 2020 despite the major setback related to the 19 closures and limitations. And these examples highlight new milestones in particle physics and pave road for future exciting results. And I hope to see you all in person in 2021, even if it's not on the beach. Thank you very much.
Thank you, Greg. Thank you for a very good talk, broader spectrum. So questions for Greg. Namit?
Yeah, hi. So you talked about R tau mu, the ratio, where LHC brought it back very close to 1. What about R tau E, or even better, if possible, tau 2 mu plus E combined?
Right. So now I don't have results on this. Let me find the results you're talking about. So this is, I think right here, test of lepton universality. Right. So, well, electrons in general are less clean than muons. So electrons radiate a lot. So looking for displaced electrons is hard because you could easily get either conversions or some photon emitted from the electron, which creates a hint of a kind of non-zero impact parameter, which is instrumental effect. So that's why this is a more complicated analysis, but I'm sure it could be done. The reason they focused on the muons is that the E-mu universality was tested at lab to a very high precision. From these previous slides, you can see it. It's actually basically right on the money and with impressive precision. So that's why they focused on the tau, and you need to compare it to just one of them. Now, the E-mu is probably possible, and we, of course, look for the Higgs decaying to E-mu, but again, indirect constraints on the lepton flavor violation or lepton flavor non-universality in the electrons and muons are much stronger, and the only one we aware about is in the B to S transitions, perhaps, which is this flavor anomaly seen by LHCb mainly. Therefore, we don't think that the heavier objects such as W's or Z's would be sensitive to this type of process, since it has been tested again at lab to very high precision. So that's why the focus was on tau and mu.
Thanks.
Okay, Gagan Mohanty.
Hi, Greg. Very nice talk. And I would have a comment on your summary slide, like the way you said slowly graduating from a young PhD student to, so senior professor. I'm really looking forward that when CMS and Atlas will take over the precision on the W mass. So would you like to bet on like when that will be? Improving on the lab precision or Tibetan on the W mass. And
right. No, Atlas has published the analysis quite some time ago, nearly 3 years ago now. And that was a tour de force analysis, which rivals Tevatron in terms of precision. CMS is still working on this analysis. And as you know, I cannot talk about the results which haven't been approved, but rest assured that there is significant effort in CMS to complete similar measurement. And I hope Atlas is also working on bigger data sets to improve on their precision.
Any further questions for Greg?
Hi, I have a small question. Can you please
go ahead?
Can you please tell me a little bit about the TAR technique that is being used in parallel with a particle flow algorithm, like in constructing this? The trackers it reclustering technique. Could you please?
Right. So basically, the idea is that tracking variables are much more precise than calorimetric measurement variables, simply because the calorimeter's typical size of the calorimeter cell is much worse than the precision achieved in the silicon tracker.
Yeah.
And therefore, if you use the tracks to enhance certain variables related to the jet, such as substructure variables, you could achieve much higher precision than by basing everything on calorimetric variables. This has been realized a long time ago in CMS. That's why CMS went fully into particle flow domain some 10 years ago, early in run one of the LHC. And Atlas, which doesn't have as high granularity of the calorimeter and tracker as CMS in run 2, uses a hybrid technique, which is this track-assisted reclustering, which essentially uses the same idea that whenever you could use tracking quantities, you replace calorimetric quantities with tracking quantities to achieve higher precision.
Okay, thank you. Thank you.
Any further questions for Greg? If not, let's thank all the three speakers, Valerie Gibson, Christophe Grojean, and Greg Landsberg, for wonderful talks in this session. So thank you all of you, and thank you all the participants for waiting till 9 p.m. in India. Thanks a lot. Bye-bye.
Thank you very much. Bye.
Thank you. Bye-bye. Thank you. Bye.